Ladies and gentlemen, good evening. On behalf of the School of Arts and Sciences, Indiana University, Purdue University, Fort Wayne, and the Institute for Advanced Studies, Indiana University, Bloomington, I wish to welcome you to this distinguished lecture of the School of Arts and Sciences, which presents Professor Richard S. Westfall, Distinguished Professor of the History and Philosophy of Science, Emeritus, Indiana University, and the 1966 Remak Distinguished Scholar of the Institute for Advanced Studies, IU Bloomington. Before Professor Westfall begins his talk, and before I introduce him, Dean David Cox of the School of Arts and Sciences would like to make a presentation to Professor Westfall.
Thank you, Gary. Professor Westfall, from time to time, usually once or twice a year, the School of Arts and Sciences, the Faculty of Arts and Sciences, recognizes a distinguished visitor as a distinguished lecturer of the School of Arts and Sciences. The Faculty of Arts and Sciences has so recognized you, and I want to give you this plaque, which will be a token of our admiration and a memento of this evening. And if you didn't notice, there is a permanent plaque that has your name engraved on it for posterity.
Oh.
Thank you very much for coming. We're honored to have you.
Thank you.
I would like to start by thanking our host departments this evening, my own Department of History and the Departments of Biology and Physics, and especially I'd like to thank the Institute for Advanced Studies, and it is through their gracious support and encouragement and nomination that Professor Westfall is able to come tonight. In the realm of ideas and the intellect, the major achievement of the second millennium of the Christian era has been the development of science and its impact on modern life and society. From its beginnings among the scholarly followers of St. Francis in the 13th century, the disciplines of science have swelled into a mighty river of achievements that have transformed the world and the cosmos. As the layman surveys this mighty work, four names stand out as preeminent among the thousands who have created the modern scientific world. And so, when at last a scientific Mount Rushmore is finally carved into stone, presumably somewhere in the gorges and hills of England, since two of the four are Englishmen, there will probably be little contention about the representation of the faces of Galileo, Newton, Darwin, and Einstein as the giants of the ages. Among the four, there will be many who will select one to be primus, and that vote will most probably go to Sir Isaac Newton of Cambridge University. Tonight, it is our great honor to have as guest lecturer the foremost authority of this century on the career and achievements of Newton. During an academic life spanning more than 4 decades, Professor Richard S. Westfall has revealed the life of Newton to this age as no other scholar has done. In his masterwork, Never at Rest, which appeared in 1980, he produced the most important biography of the English scientist. An abridged version of the biography appeared in 1993, The Life of Isaac Newton, designed to offer the insights of a lifetime study to a broader, less technically prepared audience. More generally, Dr. Westfall has written widely about the scientific revolution of the 16th and 17th centuries, in studies and books including Science and Religion in 17th Century England, 1958, and The Construction of Modern Science, Mechanisms and Mechanics, 1971, and several scores of specialized papers and studies that have appeared in scholarly journals and general encyclopedias around the world. The books about Newton and the scientific revolution have been translated into European and Oriental languages, including Italian, Spanish, Greek, Turkish, and Japanese. A native of Colorado and a graduate of Yale, where he was granted the PhD in 1955, Dr. Westfall has taught at the State University of Iowa, Grinnell College, and since 1963, Indiana University, where he became Distinguished Professor of History and Philosophy of Science in 1976. He has held many visiting posts, including Harvard, Notre Dame, Mount Holyoke, the University of Melbourne, and was a visiting fellow of Clare Hall, Cambridge, for 1 year while working on the Newton biography. The recipient of many grants and awards and honors, including Guggenheim, Rockefeller, Fulbright, and Lilly Fellowships, and several National Science Foundation grants, the Leo Gershoy Award of the American Historical Association, and twice the Pfizer Award from the History of Science Society. Dr. Westfall has also written widely on the other giant of early modern science, Galileo, and published a collection of essays on the Italian scholar in 1989 with the Vatican Publications in Rome. Tonight, Professor Westfall has promised a lecture of uncommon interest, The Scientific Revolution and the Modern World. Please join in welcoming distinguished Professor Richard Westfall to Fort Wayne.
Thank you. People in Bloomington are so misled as to think I'm just plain old Sam Westfall. As the introduction indicated, I have focused my career on the scientific revolution of the 16th and 17th centuries. The lecture tonight is not in any sense new research, but rather my effort as I approach the end of my career to look back over this subject and sum up what I think it's all about. Let me then begin with the categorical statement that the series of events that constitute the scientific revolution of the 16th and 17th centuries were crucial for the development of European history. As soon as I say that, I ought to temper it with a little scholarly caution. In my opinion, these events were crucial for the development of European history. That goes without saying. But you can measure the extent of my conviction by my readiness to announce it as empirical fact. Compare the modern world with the medieval world. We live in large centralized states. Medieval people lived in small principalities. Even where, as in England and France, fairly large monarchical states appeared, they exercised very little effective influence over the daily lives of most of their citizens. That influence was exercised at the parish level. We live in cities. Everywhere in the developed world, at least 80% of the population is urbanized. Medieval people lived in even larger proportion in tiny villages of a few hundred people. We support ourselves with large-scale industry. They supported themselves with a relatively primitive agriculture. We live in a world of machines. They lived in a world of animals and plants. Many factors stand behind the change I've attempted thus briefly to indicate. But it is a fact that there is no central feature of the modern world for which the existence of modern science is not the necessary precondition. This is especially true of what I take to be the central contrast of all. Medieval people lived in a Christian world. Christianity defined their aspirations and their view of reality. It set their standards, set the standards for their relations with others. It governed their concepts of political authority and economic value. What matters to me as a historian of science, it supplied the categories in terms of which they comprehended nature. It does not matter that no one fully lived up to the demands of the Christian ethic. It was, by definition, an ideal of perfection rather than of practicality. Nevertheless, despite the universality of imperfection, there was no one, with perhaps, and I'll underline the word perhaps, with perhaps the tiniest handful of exceptions, who doubted that he or she lived under the judgment of Almighty God, that he would be called upon to answer for his shortcomings, though she might hope to be spared because of the redemptive sacrifice of Christ Jesus. Now compare that world of the Spirit with our own. How little of it survives. Even among believers, As it happens, I have during my entire adult life been an active and committed member of a Protestant church. Claim here to be speaking from experience. Even among believers, how little it dominates our moment-to-moment consciousness. What does dominate our consciousness? Modes of thought which derive either directly or indirectly from modern science. In the Middle Ages, theology was queen of all the sciences. We have redefined the word science. Today, other disciplines seek to bolster their self-esteem by applying the word in its new definition to themselves. Thus we have social science, forensic science, management science. Death, once the ultimate province of the priest, is presided over now by the practitioners of mortuary science. Theology, the erstwhile queen, is not even allowed on the premises anymore, and a once Christian culture has become a scientific culture. The essence of the change, the hinge on which it turned, was the scientific revolution of the 16th and 17th centuries. There has been no more fundamental change in the course of European civilization, and indeed, increasingly, of world civilization. From it flow directly those capacities whereby European civilization has progressively absorbed world civilization since that time. From it stem those unique characteristics such that no other culture seems able to resist its allure. What do I mean by the scientific revolution? What is the content of this concept? I refer to a complete transformation of the scientific tradition in the West, the beginning of modern science, which is still very much with us. Do not imagine that I'm speaking of the beginning of science. There was a thriving scientific culture in Europe that reached all the way back to ancient Greece and to Aristotle. That tradition had been picked up with the revival of life in Western Europe and in the medieval universities pursued with great vigor. Once the universities were well established, there was, in a fair number of them, at any one moment, more people engaged, not solely but primarily in natural philosophy, than the total number of Greek natural philosophers we can name through the course of 7 centuries of Greek civilization. This thriving scientific culture was transformed in the 16th and 17th centuries. First of all, by heliocentric astronomy. Heliocentric astronomy marked the beginning of the scientific revolution and always remained central to it. As you no doubt know, the idea of a heliocentric system had been proposed before. Only at this time did it begin to be seriously embraced and elaborated. And by the middle of the 17th century, it was universally accepted by everyone who mattered. Accepted to the point that astronomers had trouble any longer imagining how anyone had ever thought otherwise. The heliocentric system was important on at least 4 different levels. First of all, there was the picture of the universe itself, overturning the received picture, placing the sun at the center and treating the Earth as one planet among 6, moving around the sun annually in a huge orbit. Secondly, with Kepler, heliocentric astronomy witnessed the introduction of the mechanization of nature. Astronomy before this time had been a kinematic exercise, which astronomers added up combinations of circles, deferents, and epicycles that would place the planets in theory where they were observed, in fact, to be at given times. Kepler began to treat the planets as bodies made up of common matter, similar to the matter we know, moved by the same forces that move terrestrial bodies. Third, heliocentric astronomy marked the beginning of the break with anthropocentrism. No longer was it possible to believe that everything existed for the human species. And fourth, heliocentric astronomy marked the beginning of the break with common sense that had been built into Aristotelian natural philosophy. The universe is not the way it appears to be. At every level, every one of these four levels, it was a break with the prevailing system and a significant break, a preview of the future. Closely allied with heliocentric astronomy was a transformation of the science of mechanics. That means the science of the motion of bodies. For the heliocentric system was impossible without this. As long as motion was conceived in Aristotelian terms, it was impossible that the Earth be in motion. Many of the common phenomena of motion could not possibly occur if motion were conceived in Aristotelian terms, could not possibly occur in the way we observe them to occur. Thus, early in the 17th century, there was a reconceptualization of the idea of motion, arriving at the principle of inertia. That's not a word they used, but the principle was there. The concept that a body in motion continues in motion, if nothing stops it. That motion requires no cause. That a body moving in uniform motion in a straight line is indistinguishable from a body at rest. That uniform motion in a straight line, then, is effectively identical to rest. Now, here was another assault on common sense, because this is not the way we observe bodies around us to move. And yet this principle of inertia is accepted today by philosophers of science as the fundamental concept on which the entire structure of modern science is built. More than any other one person, Galileo was responsible for the new conception of motion. What Galileo did was not limited to this. For building on the new conception of motion, he created what had never existed before, a mathematical science of terrestrial motions, that same mathematical science of terrestrial motions that all of you learned in high school physics. The mathematization of nature, as it has been called. The search for principles of geometric harmony and simplicity had been central to the new astronomy. It was now confirmed in the new science of mechanics, and together these two, astronomy and mechanics, set the mathematical character of modern science with which we are all familiar. It is significant that in Kepler and Galileo, the first of the mathematical laws of nature were announced. The idea of natural law was an old idea. A profound redefinition of what is meant by natural law was part of the scientific revolution. With the new the first of the mathematical laws of nature were announced. The idea of natural law was an old idea. A profound redefinition of what is meant by natural law was part of the scientific revolution. With the new the first of the mathematical laws of nature were announced. The idea of natural law was an old idea. A profound redefinition of what is meant by natural law was part of the scientific revolution. With the new the first of the mathematical laws of nature were announced. The idea of natural law was an old idea. A profound redefinition of what is meant by natural law was part of the scientific revolution. With the new the first of the mathematical laws of nature were announced. The idea of natural law was an old idea. A profound redefinition of what is meant by natural law was part of the scientific revolution. With the new the first of the mathematical laws of nature were announced. The idea of natural law was an old idea. A profound redefinition of what is meant by natural law was part of the scientific revolution. With the new the first of the mathematical laws of nature were announced. The idea of natural law was an old idea. A profound redefinition of what is meant by natural law was part of the scientific revolution. With the new the first of the mathematical laws of nature were announced. The idea of natural law was an old idea. A profound redefinition of what is meant by natural law was part of the scientific revolution. With the new the first of the mathematical laws of nature were announced. The idea of natural law was an old idea. A profound redefinition of what is meant by natural law was part of the scientific revolution. With the new the first of the mathematical laws of nature were announced. The idea of natural law was an old idea. A profound redefinition of what is meant by natural law was part of the scientific revolution. With the new the first of the mathematical laws of nature were announced. The idea of natural law was an old idea. A profound redefinition of what is meant by natural law was part of the scientific revolution. With the new the first of the mathematical laws of nature were announced. The idea of natural law was an old idea. A profound redefinition of what is meant by natural law was part of the scientific revolution. With the new the first of the mathematical laws of nature were announced. The idea of natural law was an old idea. A profound redefinition of what is meant by natural law was part of the scientific revolution. With the new the first of the mathematical laws of nature were announced. The idea of natural law was an old idea. A profound redefinition of what is meant by natural law was part of the scientific revolution. With the new the first of the mathematical laws of nature were announced. The idea of natural law was an old idea. A profound redefinition of what is meant by natural law was part of the scientific revolution. With the new of the mathematical laws of nature were announced. The idea of natural law was an old idea. A profound redefinition of what is meant by natural law was part of the scientific revolution. With the new the first of the mathematical laws of nature were announced. The idea of natural law was an old idea. A profound redefinition of what is meant by natural law was part of the scientific revolution. With the new the first of the mathematical laws of nature were announced. The idea of natural law was an old idea. A profound redefinition of what is meant by natural law was part of the scientific revolution. With the new the first of the mathematical laws of nature were announced. The idea of natural law was an old idea. A profound redefinition of what is meant by natural law was part of the scientific revolution. With the new the first of the mathematical laws of nature were announced. The idea of natural law was an old idea. A profound redefinition of what is meant by natural law was part of the scientific revolution. With the new the first of the mathematical laws of nature were announced. The idea of natural law was an old idea. A profound redefinition of what is meant by natural law was part of the scientific revolution. With the new the first of the mathematical laws of nature were announced. The idea of natural law was an old idea. A profound redefinition of what is meant by natural law was part of the scientific revolution. With the new the first of the mathematical laws of nature were announced. The idea of natural law was an old idea. A profound redefinition of what is meant by natural law was part of the scientific revolution. With the new the first of the mathematical laws of nature were announced. The idea of natural law was an old idea. A profound redefinition of what is meant by natural law was part of the scientific revolution. With the new the first of the mathematical laws of nature were announced. The idea of natural law was an old idea. A profound redefinition of what is meant by natural law was part of the scientific revolution. With the new the first of the mathematical laws of nature were announced. The idea of natural law was an old idea. A profound redefinition of what is meant by natural law was part of the scientific revolution. With the new the first of the mathematical laws of nature were announced. The idea of natural law was an old idea. A profound redefinition of what is meant by natural law was part of the scientific revolution. With the new the first of the mathematical laws of nature were announced. The idea of natural law was an old idea. A profound redefinition of what is meant by natural law was part of the scientific revolution. With the first of the mathematical laws of nature were announced. The idea of natural law was an old idea. A profound redefinition of what is meant by natural law was part of the scientific revolution. With the first of the mathematical laws of nature were announced. The idea of natural law was an old idea. A profound redefinition of what is meant by natural law was part of the scientific revolution. With the first of the mathematical laws of nature were announced. The idea of natural law was an old idea. A profound redefinition of what is meant by natural law was part of the scientific revolution. With the first of the mathematical laws of nature were announced. The idea of natural law was an old idea. A profound redefinition of what is meant by natural law was part of the scientific revolution. With the first of the mathematical laws of nature were announced. The idea of natural law was an old idea. A profound redefinition of what is meant by natural law was part of the scientific revolution. With the first of the mathematical laws of nature were announced. The idea of natural law was an old idea. A profound redefinition of what is meant by natural law was part of the scientific revolution. With the first of the mathematical laws of nature were announced. The idea of natural law was an old idea. A profound redefinition of what is meant by natural law was part of the scientific revolution. With the first of the mathematical laws of nature were announced. The idea of natural law was an old idea. A profound redefinition of what is meant by natural law was part of the scientific revolution. With the first of the mathematical laws of nature were announced. The idea of natural law was an old idea. A profound redefinition of what is meant by natural law was part of the scientific revolution. With the first of the mathematical laws of nature were announced. The idea of natural law was an old idea. A profound redefinition of what is meant by natural law was part of the scientific revolution. With the first of the mathematical laws of nature were announced. The idea of natural law was an old idea. A profound redefinition of what is meant by natural law was part of the scientific revolution. With the first of the mathematical laws of nature were announced. The idea of natural law was an old idea. A profound redefinition of what is meant by natural law was part of the scientific revolution. With the new of the mathematical laws of nature were announced. The idea of natural law was an old idea. A profound redefinition of what is meant by natural law was part of the scientific revolution. With the new the first of the mathematical laws of nature were announced. The idea of natural law was an old idea. A profound redefinition of what is meant by natural law was part of the scientific revolution. With the first of the mathematical laws of nature were announced. The idea of natural law was an old idea. A profound redefinition of what is meant by natural law was part of the scientific revolution. With the first of the mathematical laws of nature were announced. The idea of natural law was an old idea. A profound redefinition of what is meant by natural law was part of the scientific revolution. With the first of the mathematical laws of nature were announced. The idea of natural law was an old idea. A profound redefinition of what is meant by natural law was part of the scientific revolution. With the first of the mathematical laws of nature were announced. The idea of natural law was an old idea. A profound redefinition of what is meant by natural law was part of the scientific revolution. With the first of the mathematical laws of nature were announced. The idea of natural law was an old idea. A profound redefinition of what is meant by natural law was part of the scientific revolution. With the first of the mathematical laws of nature were announced. The idea of natural law was an old idea. A profound redefinition of what is meant by natural law was part of the scientific revolution. With the first of the mathematical laws of nature were announced. The idea of natural law was an old idea. A profound redefinition of what is meant by natural law was part of the scientific revolution. With the first of the mathematical laws of nature were announced. The idea of natural law was an old idea. A profound redefinition of what is meant by natural law was part of the scientific revolution. With the first of the mathematical laws of nature were announced. The idea of natural law was an old idea. A profound redefinition of what is meant by natural law was part of the scientific revolution. With the first of the mathematical laws of nature were announced. The idea of natural law was an old idea. A profound redefinition of what is meant by natural law was part of the scientific revolution. With the new the first of the mathematical laws of nature were announced. The idea of natural law was an old idea. A profound redefinition of what is meant by natural law was part of the scientific revolution. With the new the first of the mathematical laws of nature were announced. The idea of natural law was an old idea. A profound redefinition of what is meant by natural law was part of the scientific revolution. With the new astronomy and the new mechanics, among that small number of people who understood what was going on, Aristotelian natural philosophy had become untenable. And if the nascent scientific revolution were to continue further, it was essential that a new philosophy of nature be elaborated. One was. Historians refer to it as the mechanical philosophy. It was primarily the work of the French philosopher René Descartes. The mechanical philosophy universalized that rejection of common sense. It's not just the heavens that are not as they appear to be. It's not just motion which is not as it appears to be. Nothing is as it seems to be. We see about us a world full of life, full of qualities. They're all illusions. There's nothing out there except particles of inert matter in motion. The world could hardly be more different than it appears to be. Now, at the end of the 17th century, Isaac Newton picked up these various strands I've referred to, and elaborated them in a fundamental way, adding a new principle to the fundamental ontology of nature. It's not just particles of inert matter, but particles of inert matter moved by interparticular forces. Those forces were mathematically defined. With this concept, Newton was able to draw together celestial motions and terrestrial mechanics in one overarching mathematical synthesis. With Newton, the new science and the new philosophy of nature reached their definitive form in which they would shape Western science for the coming 2 centuries. In the 20th century, the system has been much modified. I think the crucial word to use is modified, not transformed, because in its modified form, that 17th century system still seems to me to reign. It absolutely dominates modern thought. One can see no prospect of the end of its domination. Equally, the scientific revolution embodied changes in method associated with experimental procedure. The concept of experiment was not new in the 17th century. There were legitimate experiments performed earlier. Nevertheless, when the 17th century dawned, experimentation was not seen, not even close to seen, as the distinctive procedure of science. By the end of the century, it was recognized that way. The century witnessed several startling demonstrations of its power. For example, there was the international investigation spread over the middle of the century that began with Galileo's discussion of why pumps don't operate above 32 feet, passed through the works of the Italian Torricelli, the Frenchman Pascal, and ended up with the Englishman Robert Boyle and Boyle's law, another of the early mathematical laws of science. Or there was Newton's investigation of the heterogeneity of light and the phenomena of colors, which also pursued a mathematical law, although in the end that one didn't work out. But it was an investigation, experimental all the way. Science had never witnessed anything like these two or other investigations before. In the future, it would witness hardly anything that was unlike them. And finally, I would say that the scientific revolution introduced a new relation between science and Christianity. Now, this is a subject that needs to be discussed with some care. The religious proclivities of 17th century scientists are well known, and there's no way in which I wish to deny them. As it appears to me, the net result of all their efforts to demonstrate the existence of God from the phenomena revealed by the new science, the net result, I say, was to separate science from revealed theology. From the point of view of science, we might say to liberate science from revealed theology. Several centuries earlier, as European civilization took shape out of the chaos of the Dark Ages, Christian theology had nurtured, molded, and hence dominated every creative activity in that new civilization. Now, by the end of the 17th century, science was asserting its autonomy. Compare two incidents. Early in the 17th century, the Catholic Church, led primarily by Cardinal Roberto Bellarmino, condemned Copernican astronomy because of its conflict with the overt meaning of several passages in Scripture. 65 years later, Isaac Newton and Thomas Burnet carried on a brief correspondence about Burnet's book, The Sacred Theory of the Earth. In that book, Burnet had argued that the account in Genesis of the formation of the earth could not possibly be a true philosophical account, that it was a fiction composed by Moses for political purposes. In the correspondence, Newton defended the book of Genesis, arguing that what it had to say was what science, which in the context of this correspondence really meant chemistry, would lead us to expect. Now compare the assumptions of both Burnet and Newton in that correspondence with the assumption of Bellarmino at the beginning of the century. For Bellarmino, Scripture determines what is acceptable in science. Both Burnet and Newton are using science to determine what is acceptable in Scripture. An exact reversal of the positions of authority, and that reversal has never been reversed anew. Let me briefly examine the process by which all of this happened. As I perceive it, from Copernicus' question, in the middle of the 16th century, we have an ever-widening domain of discussion. The proposition that the earth is in motion leads on to the examination of the phenomena of motion in general. Then it becomes necessary to re-examine the whole of natural philosophy. And so it proceeded, with the domain of discussion becoming ever broader. What spurred this discussion on? Historians of science debate that. There was an old tradition in the history of science, deified scientists, or if that word's perhaps too strong, sanctified them. No historian thinks that that's good history. I certainly regard myself as a historian. Thus, I want to avoid anything like that. An alternative view, particularly popular among young scholars in the field, is to view science as the product of social forces, in this case primarily the appearance of a new capitalist economy. I'm not exactly one of the young scholars in the field, and to me it appears difficult to sustain that argument when one gets down to details. What I perceive is a discussion going on, but not spurred primarily by any pursuit of practical utility. Mankind has always sought to understand the world in which we live. Without in any way deifying or sanctifying the scientists, I want to make that pursuit of understanding central to the process. I think of Kepler, a man without personal resources, dependent through his whole life on patrons, always aware that today's patron is mortal, and thus always on the lookout for the next one. But willing to live in this way, teetering, as it appears to me, eternally on the verge of oblivion, if he might have the privilege of demonstrating the correct pattern of the heavens. Or I think of Galileo, who was ready to dare the fury of the Inquisition because it mattered whether the universe were geocentric or heliocentric. But especially, I see this process at work in Newton, who is the figure I know best. Late in the year 1684, Newton received a visit from the astronomer Edmund Halley, who put to him the following question: what would be the shape of the orbit of a body that circles another, which attracts it with a force that varies inversely as the square of the distance? This was not a new question to Newton. It was a question that arose exactly out of that expanding domain of inquiry, and Newton had put it to himself some 20 years earlier. And more recently than that, in a correspondence with Robert Hooke. But Newton was a man of many interests. For a bit over a decade before the visit from Edmund Halley, he had almost entirely abandoned mathematics, mechanical science, to devote himself on the one hand to alchemy and on the other hand to theology. For more than a decade he had hardly touched those topics we associate with his name. But then Halley arrived at his door. I don't know any other way to put this. The problem that Halley put grasped him and would not let him go. In the years ahead, there were stories floating around Cambridge about the strange fellow who lived next to the great gate of Trinity College. The other fellows of the college, an uninspired lot, if you could ever find one, were half amused by this strange man, half in awe of him, who would come out of his chamber on the way to the hall for dinner, take the wrong turn, find himself out on the street of Cambridge, not able to recollect why he was out there. He'd go back to his room, skip dinner. Or he might get to the hall wearing the wrong gown. I'm not sure what the wrong gown was, but they do. His hair disheveled, and then he'd sit there, lost in thought, while the meal cooled on the plate in front of him. You wouldn't believe how many stories survive from the 17th century of Newton forgetting to eat his meals. Clearly, food was a matter of some significance then. They would hear from his chamber fellow or servant that he would forget to sleep as well. When they walked in the gardens of Trinity College, they would find strange geometric diagrams drawn in the sand. It says something about the awe that he inspired, that they would walk around these diagrams and they'd stay there until the rain erased them. Newton cut himself off completely. Only about 2 letters survive from the following 2.5 years, and those letters are associated with the inquiry he was engaged in. We don't know anything about his life. Or maybe I want really to put it exactly the other way. We know everything about his life. That is to say, it was all writing a book. And he had no life except for that. And through his manuscripts, which survive, we can follow his progress. And again, what we find is a constantly expanding domain of discussion. First, there was the problem that Halley put to him, the dynamics of orbital motion. And at the end of 1684, Edmund Halley received a pamphlet of about 10 pages sketching out an orbital dynamics. Very similar to the first 3 sections of Book 1 of the Principia. But even then, the problem had another dimension for him. Let me put that other dimension in terms of the well-known Newtonian story about the fall of an apple. The dimension was the correlation between the fall of bodies on the surface of the earth and terrestrial motions. Galileo had asserted that all heavy bodies fall with the same rate of uniform acceleration. It occurred to Newton that he could try this with an accuracy no one had ever tried before by means of pendulums, which successive swings would add up even tiny differences. In his notes we find, incidentally, this passage in exactly these words makes its way into the published Principia, that he tried it with gold, silver, lead, glass, sand, salt, water, wood, and wheat, all functioning as the bob on a pendulum. And all of those pendulums, whatever the material, if they were of the same length, had the same period. That was only possible if all of the particles of those different substances were equally attracted by the earth. And then he began to see that God was performing the same experiment for him in the heavens. For if the satellites, or if the planets observed Kepler's third law, then the sun must attract them, or attract all their particles exactly in the same way. And if the satellites of Jupiter observed Kepler's third law, then Jupiter must attract them in exact proportion to their amount of matter. And if the satellites of Jupiter remain concentric around Jupiter as they are observed to do, then the sun must attract both them and Jupiter in exact proportion to their quantities of matter. In the early months of 1685, the principle of universal gravitation silently unfolded before Newton's penetrating gaze. Clearly, this demanded more than a pamphlet of 10 pages. During 1685, he expanded it into a manuscript roughly 10 times as long, in which he demonstrated the phenomenon of the heavens on the assumption that there is an attracting body at the center of our system. But the principle of universal gravitation demanded that if the sun attracts the planets attract the sun and attract each other as well. And it was necessary for Newton to show that all these mutual attractions would not upset Kepler's third law, or Kepler's three laws, which function for him as sort of empirical controls. He approached this, first of all, in terms of the two-body problem, the sun and one planet. And he demonstrated that the mutual attractions between the two would, for a given intensity of force, change the size of the orbits and the periods, but not upset Kepler's three laws. But of course, the universe is not made up just of a sun and one planet. The issue was, would not the mutual attraction of the many bodies upset this? Now, this is a problem that Newton did not succeed in submitting to analytic solution. Indeed, it's been shown in the 20th century that the problem is incapable of analytic solution. But Newton did arrive at a treatment of the three-body problem, which allowed him to argue reasonably that the mutual attractions, let me put in, initially the three bodies were one planet, let's say Mercury, and then a third planet outside of Mercury. And he proceeded by breaking the attraction of the outside planet on Mercury down into two components, one radial to the orbit of Mercury and the other between the sun and the external planet. He was able to argue on the basis of that analysis that under the conditions that do exist, which is to say large distances in relationship to the orbit, to the radius of an orbit, and small angles, most perturbations would fall below the limit of terrestrial, below the threshold of terrestrial observation in such a universe as ours. Then he saw he could take this analysis, develop to show that most perturbations fall below the threshold of observation as it then stood. He could take this analysis, turn it inside out, and use it to submit some perturbations that were capable of observation to exact quantitative treatment. This analysis then became the basis of a new approach to the moon. Now the central body is the Earth, and the external perturbing body is the sun. This analysis, astronomers had established empirically before this time various strange aspects of the moon's motion. Newton arrives at an exact quantitative derivation of those perturbations. But the orbiting body might be a channel of water around the Earth. The external perturbing body would now be the combination of the moon and the sun. That analysis became the basis of the first successful explanation of the tides. Or the orbiting body might be the heap of matter at the equator of the Earth arising from the rotation of the Earth. And again, it's the sun and the moon that attract this. And with this he explained, also in exact quantitative terms, a conical motion of the Earth's axis that gives rise to a celestial phenomena called precession of the equinoxes. One has here then, in the final form that the Principia reached, not just the principle of universal gravitation, although that's pretty significant in itself, but a whole new ideal of science. Before this time, science had treated ideal cases, ignoring small deviations which arose, they argued, from the imperfections of matter. with Newton, those small deviations begin to be submitted to exact quantitative treatment. It's instructive to read the popularizations of Newtonian science that were published in the early 18th century. One and all, they insist on the strangeness of the Newtonian world. The strangeness well beyond that of the mechanical philosophy. For the world is not just a machine. It is, if I can put it this way, an immaterial machine, or almost an immaterial one. For as Newton pursued the principle of attraction, matter gradually dissolved away almost to nothing. Gravitation was not the only attraction he recognized. He was convinced there were several short-range attractions between particles. And in the end, the attractions became everything, and the particles nothing. One of those popularizers put it in the following way: if all the solid matter in the universe were compacted together, it would not fill a nutshell. To that extent, mankind in the West had moved away from the familiar world of daily experience in the short space of about 150 years. It's instructive also to look at the religious situation. I did insist upon this at the beginning. Everyone I have brought up was a believing Christian. Most of them you would describe as pious. Nevertheless, it does appear to me that by the end of the 17th century, there had ceased to be what had existed in the earlier system, a close filiation between the intellectual constructs of their science and their piety. Some, I have Newton primarily in mind, had begun actively to question aspects of Christianity. I have the doctrine of the Trinity primarily in mind, which seemed to him irrational. In fact, it seems to me, the rise of modern science had undercut the foundation on which, until that time, Christianity had traditionally rested. It was no accident that within decades, men such as Hume and Dolbach would take their questioning far beyond anything that Newton was willing to consider. The conversion of a Christian civilization into a scientific one does appear to me as a necessary, as an inevitable consequence of the scientific revolution. And now, in the 20th century, we live still in that altered world. Intellectually, it has become steadily less familiar and steadily more ominous. And there have been practical consequences as well. For slowly in the 18th century, then with greatly increased speed in the 19th century, science became the foundation of a new technology that accelerated the exploitation of non-renewable resources until we stand today face to face with their exhaustion. A technology that produced new products that nature is unable to assimilate, so that we are beginning to choke on our refuse. A technology that produced instruments of destruction more terrible than any earlier age even dreamed of. Now that's a deliberately partial list of the outcome of that technology, made deliberately partial in order to relate it to the voices of protest against science. But you cannot have failed to hear any number of people who have trouble sustaining a connected discourse of more than 3 sentences, sorry. You get a historian here and this is what happens. Are prepared to tell us that modern science is a mistake. We have more truth, apparently, than we can cope with. Well, now, you can possibly conclude from the language I've chosen to use that I'm unwilling even to entertain that thought. And the concept of truth does seem to me central. Truth is a difficult proposition in modern science. I have been for more than 30 years a member of a Department of History and Philosophy of Science. And I'm bold enough to say that I understand the difficulties in that concept as well as anyone here. I want to use a form of language meant to get around the apparently insoluble problem of verification, which is not the one I want to concern myself with, and say that there remains a meaningful sense of the word true, in terms of which I find it impossible to deny that modern science is true. The idea that it's just the ideology of a given class is so absurd that one wonders how any serious person can entertain it. Rockets fired to go to the moon do arrive at the moon. Reactors at Chernobyl and 3 Mile Island designed to generate heat do generate heat. Materials designed to destroy life released into the atmosphere at Westfall do destroy life. Now, I've deliberately mentioned those disasters lest anyone think that I don't take the problems modern technology has brought for us seriously. The problems seem to me enormous. But the problems cannot invalidate the science. Indeed, quite the contrary, the problems wouldn't exist if the science behind that technology did not correspond to reality. It does seem to me that the only possible solution to those problems is through further application of science. We in the West have known since the age of the Greeks that knowledge can be suffering. The scientists of the 17th century were willing to entertain the awful thought that the universe had not been created for them and was not proportioned to them. 3 centuries have accustomed us to that thought, and our problems are primarily the need to cope with material consequences. It does appear to me that the critics of science are taking for granted the benefits that science has brought and dream of simply rejecting its ills. But it's all one fabric. Before we throw it away, we might pause to wonder wherewith we will cover our nakedness. Do we really want to surrender that ease of communication and travel which have so enhanced the life of everyone in this room? Do we really want to do without that deliverance from illness and pain? That blessed deliverance from illness and pain, which every culture in the world has pursued, but only the culture that gave birth to modern science has achieved. But more important than these, do we want to surrender that enormous increase in understanding that has come with modern science? What sort of intellectuals are they who would contemplate surrendering the knowledge gained at the cost of so much effort? If knowledge is suffering, truth is liberation, liberation from ignorance. And it's in these terms that I see the ultimate harmony of modern science with Western civilization. It's in these terms that I see science not as some claim as an aberration of that civilization, but rather as a fulfillment of one of its most fundamental themes. About 2,500 years ago, Plato closed his Republic with the myth of a myth of souls in the cycle of transmigration, returning to a new life after a 1,000-year interval of reward or punishment for the previous life. And at the last moment before they return to a new life, they are granted a glimpse of a representation of the universe, the unconscious memory of which will be the foundation of the knowledge they gain in the life they are beginning. Significantly, it seems to me, Plato calls that representation of the universe the spindle of necessity, by which I take him to be saying that we're not free to ignore reality. Of all the generations of the human species, it was given most to the scientists of the 17th century to view the spindle of reality, spindle of necessity. Not only did that view change the course of European civilization, but I would submit to you that it was in itself one of the greatest moments in the history of the species. I thank you.